You think you're solid. You think the chair you're sitting on is solid. You think matter is stuff, tangible, substance-filling space. But you're wrong. You are almost entirely empty space. The atoms that make up your body, the atoms in the chair, the atoms in everything around you are 99.9% empty. If an atom were the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be tiny specks orbiting at the outer walls. Everything in between, the entire volume of the stadium, is nothing. Empty. Void. Yet, you don't fall through the chair, you don't collapse into a point. Solid matter feels solid. How is this possible? How can something that's almost entirely empty space behave like it's solid? I'm Leonard Susskind, and I've spent 50 years thinking about quantum mechanics and the structure of matter. And I'm going to tell you why atoms are empty, why that emptiness doesn't mean what you think it means, and why the solidity you experience is the strangest illusion in physics. Let me start with the numbers. An atom is about 10 to the minus 10 meters across, 1 angstrom, a 10 billionth of a meter. The nucleus at the center is about 10 to the minus 15 meters across, a femtometer. That's 100,000 times smaller than the atom. If you scale up an atom to the size of a football stadium, 100 meters across, the nucleus is about a millimeter. Smaller than a grain of rice, the rest of the atom, the vast majority of the volume, contains only electrons. And electrons are point particles. They have no measurable size. They're smaller than we can detect. So the atom is a tiny nucleus surrounded by a vast empty space where electrons exist. But here's the crucial point. The electrons are not orbiting the nucleus like planets orbit the sun. That's the Bohr model from 1913. It's wrong. Electrons don't have definite positions. They exist in quantum clouds, probability distributions around the nucleus. The electron cloud defines the size of the atom, but the cloud itself is not made of substance. It's made of probability. In quantum mechanics, particles don't have definite positions until you measure them. Before measurement, an electron is in a superposition spread out over space according to its wave function. The wave function gives probabilities for where you might find the electron if you look. High probability regions are where the electron is likely to be found. Low probability regions are where it's unlikely. But until you measure, the electron doesn't have a position. It's not hiding somewhere in the cloud waiting to be found. It genuinely doesn't have a definite location. This is not a limitation of measurement. It's fundamental to quantum mechanics. Position is not a property the electron has before measurement. When you do measure, the wave function collapses and you find the electron at some location. But before measurement, it was spread out. This spreading is not because the electron is moving around really fast. It's because the electron is genuinely delocalized. It exists as a probability cloud. So an atom is a nucleus, a tiny dense core of protons and neutrons surrounded by electron clouds that define the atom's size. And these clouds are not material. They're quantum mechanical probability distributions. The atom is almost entirely empty in the sense that almost all the volume contains no matter, just probability. Yet this empty atom is what makes up solid objects. How? The answer is forces, specifically electromagnetic forces. When you touch a table, when you sit on a chair, what you're feeling is not atoms physically colliding like billiard balls. What you're feeling is electromagnetic repulsion between the electron clouds of the atoms in your hand and the atoms in the table. Electrons are negatively charged. Like charges repel. As your hand approaches the table, the electron clouds of your atoms get close to the electron clouds of the table's atoms. They repel each other. The force increases as they get closer. At some point, the repulsion balances the force you're applying with your hand. You feel resistance. This is what solidity is, electromagnetic repulsion. You never actually touch the table. Your atoms never contact the table's atoms. The electron clouds repel before that happens. There's always a tiny gap, a few angstroms, between your atoms and the table's atoms, filled with electromagnetic fields pushing back. This is true for everything. You've never touched anything in your life, not in the sense of making contact. You've always been separated by electromagnetic forces. The floor holds you up, not because it's solid in some material sense, but because the electromagnetic repulsion between your atoms and the floor's atoms is strong enough to counteract gravity. If electromagnetic forces were weaker, you'd sink through the floor. If they were stronger, you couldn't compress materials at all. The strength of electromagnetic forces determines how matter behaves. And these forces operate between objects that are mostly empty. Now let me tell you about the nucleus. If atoms are mostly empty, nuclei are incredibly dense. A nucleus contains almost all the mass of the atom in a tiny volume. Protons and neutrons are packed together. The density is about 10 to the 17 kilograms per cubic meter. A sugar cube of nuclear matter would have a mass of about 100 million tons. Neutron stars are made of this material. The entire star is essentially one giant nucleus. Neutron stars have masses similar to the Sun compressed into a sphere 20 kilometers across. This is possible because atoms are mostly empty. Crush atoms together hard enough and you squeeze out the empty space. The electron clouds collapse. Electrons combine with protons to form neutrons. You're left with pure nuclear matter. But normal matter, at normal densities, is kept from collapsing by the electromagnetic forces between atoms. The emptiness is preserved by repulsion. Let me address a common question. If atoms are empty, why does matter have volume? Why doesn't everything collapse into a tiny dense nucleus? The answer is quantum mechanics again. Specifically, the Heisenberg uncertainty principle and the Pauli exclusion principle. The uncertainty principle says that the more you confine a particle in space, the more uncertain its momentum becomes. If you squeeze an electron into a tiny region, its momentum must be large and uncertain. This means it has high kinetic energy. Confining electrons costs energy. At some point, the energy cost of confining electrons balances the energy gain from electromagnetic attraction. Atoms reach an equilibrium size where these energies balance. This is why atoms have the size they do. About an angstrom. If you try to compress an atom, you increase the kinetic energy of the electrons. They push back. This is called degeneracy pressure. It's a quantum mechanical effect with no classical analog. The Pauli exclusion principle says that no two fermions can occupy the same quantum state. Electrons are fermions. They obey Fermi-Dirac statistics. This means you can't put all the electrons in an atom into the lowest energy state. They have to stack up in different states, different orbitals with different energies. This is why atoms have complex electron shells. The first two electrons go into the 1s orbital, the next two into the 2s, then 6 into the 2p, and so on. The Pauli principle prevents electrons from all collapsing into the nucleus. It forces them to occupy a volume. This is another reason atoms have size. Without the Pauli principle, all electrons would fall into the lowest energy state right at the nucleus. Atoms would be much smaller, matter would be denser, chemistry would be completely different. Life wouldn't exist. Now let me tell you about quantum field theory. In quantum field theory, particles are excitations of fields. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. These fields permeate all of space. So in a sense, empty space is not empty. It's filled with fields. All the fundamental fields, electron field, quark fields, photon field, Higgs field, and so on. Particles are just disturbances in these fields. A localized bump in the field is what we call a particle. So when we say an atom is mostly empty, we mean it's mostly field in its ground state. No particles, no disturbances, but the fields are there. always, everywhere. And these fields have quantum fluctuations, virtual particles constantly appearing and disappearing. The vacuum is not a static nothing. It's a dynamic, seething foam of quantum activity. At scales smaller than we can detect, space is filled with virtual particle pairs popping in and out of existence. This raises a philosophical question. What is empty? In classical physics, empty space is just absence, nothing there. But in quantum field theory, empty space is filled with fields and fluctuations. It has structure, it has energy, the vacuum has a vacuum energy, the cosmological constant. Empty space pushes on itself, causing the universe to expand. So the emptiness in atoms is not classical nothingness, it's quantum field vacuum. Still empty in the sense of no particles, but not empty in the sense of pure nothingness. There's something there. Fields, potential, quantum foam. Now let me talk about why the emptiness matters. The fact that atoms are mostly empty explains many phenomena. Transparency, for example. Light passes through glass because glass atoms are mostly empty. Photons travel through the empty space between nuclei. Occasionally, a photon interacts with an electron and gets absorbed or scattered. But most photons pass through unimpeded. If atoms were solid, opaque objects, light couldn't penetrate, everything would be opaque. Radioactivity works because of the emptiness. Alpha particles, helium nuclei, can tunnel out of larger nuclei and escape. They pass through the mostly empty atomic structure of surrounding material. Beta particles, high-energy electrons, also escape because atoms don't block them. Most of the atom is empty, so high-energy particles can pass through. This is why we need thick shielding for radiation. You need enough atoms, enough statistical chance of interaction to stop high-energy particles. A thin sheet of material is mostly empty space and particles zip through. Chemical bonding depends on the electron clouds overlapping. When atoms approach, their electron wave functions can overlap. The electrons become shared between nuclei. This lowers the energy. The atoms bond. Molecules form. All of chemistry, all of biology, depends on the quantum mechanical behavior of electron clouds in the mostly empty volume of atoms. If atoms were solid billiard balls, chemistry wouldn't work. There would be no molecules, no life. Let me tell you about neutron scattering experiments. Neutrons are uncharged, so they don't interact electromagnetically with electron clouds. They pass through atoms easily. They only interact with nuclei through the strong nuclear force. So neutrons can probe the structure of matter by passing through and occasionally scattering off nuclei. These experiments confirm that atoms are mostly empty. Neutrons travel through centimeters of solid material before hitting a nucleus. The probability of scattering is tiny because nuclei occupy such a small fraction of the volume. If atoms were dense throughout, neutrons would scatter immediately. But they don't. They confirm the nuclear model. Tiny, dense nuclei in vast, empty space. This is also why neutrinos are so hard to detect. Neutrinos interact only through the weak nuclear force, even weaker than the strong force. They pass through entire planets without interacting. Trillions of neutrinos from the sun pass through your body every second. None of them interact. They go straight through the empty space in your atoms. Occasionally, very rarely, a neutrino hits a nucleus, and we detect it. But most of the time, neutrinos see the universe as empty. Now let me address the philosophical implication. If you're mostly empty space, in what sense are you real? What is solid if not material substance? The answer is that reality is not what we intuitively think. Solid is not substance. Solid is electromagnetic forces. You are real. You exist. But you're not made of continuous stuff. You're made of quantum fields with localized excitations we call particles, And these particles are mostly separated by vast empty space with forces between them. Your experience of solidity is forces, not substance. This is a radical shift in understanding. For thousands of years, humans thought matter was continuous, solid, substance. Democritus proposed atoms, indivisible particles of matter. But even atoms are not solid, they're mostly void, and the particles inside, protons, neutrons, electrons, are not solid either. Protons and neutrons are made of quarks. Quarks and electrons are point particles. No size, no structure, just mathematical points with properties like charge and mass. If you could zoom in infinitely on matter, you'd never find solid substance. You'd find fields and forces. Mathematics, not stuff. Let me tell you why this matters for quantum mechanics. The emptiness of atoms is intimately connected to the wave-particle duality. Electrons are not tiny balls orbiting a nucleus. They're quantum objects described by wave functions. And wave functions spread out over space. The electron cloud is the wave function. The emptiness is necessary for quantum behavior. If electrons had definite positions and trajectories, if atoms were solid objects, quantum mechanics wouldn't work, interference wouldn't happen, superposition wouldn't exist, tunneling would be impossible. The emptiness allows quantum phenomena. And here's something truly strange. The size of atoms is determined by fundamental constants. The Bohr radius, the typical size of an atom, is about 0.5 angstroms. This is determined by the electron mass, the electron charge, Planck's constant, and the permittivity of free space. Change these constants and atoms would be different sizes. If the electron were heavier, atoms would be smaller. If the electromagnetic force were stronger, atoms would be smaller. The emptiness of atoms is not arbitrary. It's determined by the laws of physics. And here's another strange fact. The emptiness scales. Nuclei are mostly empty too. They're made of protons and neutrons. Protons and neutrons are made of quarks. Quarks are held together by gluons. But most of the proton's volume is empty. The quarks are point particles. The strong force fields between them fill the space. So protons are like tiny atoms. Dense point-like particles, quarks, surrounded by force fields in mostly empty space. And this pattern might continue. If quarks are made of smaller constituents, those constituents would be surrounded by emptiness. All the way down, matter at every scale is mostly empty. Only the forces between particles give it structure. Let me end with what the emptiness teaches us about reality. The universe is not made of substance. It's made of fields and particles governed by forces. The solidity you experience is electromagnetic repulsion between quantum clouds. The matter you touch is almost entirely void. You are walking on emptiness held up by forces. This is not an illusion in the sense that it's false. The forces are real, the structure is real, but it's not what we intuitively imagine. Solid is not continuous material. Solid is quantum mechanical force fields. After 50 years of thinking about quantum mechanics, I've come to accept that reality at the fundamental level is profoundly different from our everyday experience. We evolved to perceive solidity because it's useful for survival, but the underlying reality is emptiness and forces. Atoms are almost entirely empty. You are almost entirely empty, and yet here you are. Solid, real, thinking, conscious, existing as a pattern of forces and fields in mostly empty space. That's what quantum mechanics reveals. That's what atoms are. Empty but not meaningless. Void but not absent. Almost nothing but somehow everything. Thank you for watching. Now you know what you're really made of. Welcome to the quantum vacuum.